It turns out we need to tweak a few of our equations that we learned in Physics 1. One of them is the equation for momentum. Recall that in Physics 1 we learned that the momentum of a particle was a vector and it depended on the mass and the velocity. Well, in relativistic momentum, momentum is still a vector, but this equation no longer works. In relativity, we need to add this extra term. And so in relativity, our momentum is the classical relativity, and again, remember that u is the variable we are using for the velocity of an object in the unprimed reference frame. So this is the momentum of just an object in some reference frame. To be clear, we're not transforming momentum from one reference frame to another with this equation. We're just calculating the momentum in a reference frame. If we wanted to calculate what it was in a different reference frame, we would need to figure out what its velocity was in that reference frame, and then we'd be able to use this equation to calculate it. So the momentum of an object in some reference frame is mass times its velocity in that reference frame divided by 1 minus its velocity squared over c squared. Notice that once again, if u is very small, then this ends up just looking like our regular classical Newtonian momentum. So we could think of the momentum that we learned about last semester as being a special case of a momentum. That momentum equation that we learned last semester is a special case of the momentum when the velocity is low, small compared to the speed of light. We'll often use this gamma, and this gamma is 1 over the square root of 1 minus the velocity squared over c squared. What gamma kind of tells us is how relativistic is this particle. If we get a gamma very close to 1, then we say, oh, well, it's not very relativistic. We can probably use a classical model for this particle. But if we got a gamma of 4 or 5 or 6 or even higher, then we know that this is a highly relativistic particle, and any classical mechanics type calculations are likely to be incorrect. So written in terms of this gamma, we have that the momentum equals gamma mu. Let's see what that looks like if we graph it. So if we graph momentum here versus the speed here, so on our vertical axis we have momentum, on the horizontal axis we have speed. The Newtonian momentum just rises linearly. The faster an object goes, the greater the momentum. However, the relativistic momentum, we see that at slow speeds, something like below half the speed of light, they line up perfectly. And so when we're calculating the momentum of a school bus or an airplane, we just don't have to worry about relativity. However, as we think about things that are moving faster and faster and faster, then we do have to start including them. So this is why you haven't noticed these effects. This is why your common sense isn't prepared to immediately understand these effects, because you live in this world down here of small speeds. And relativity only becomes really a significant factor when you start getting above about a half of the speed of light. So notice another interesting thing about this, and that is that as you approach the speed of light, what happens to the momentum? The momentum approaches infinity. In other words, what is the momentum of an object moving at the speed of light? It's infinity. Well, we can't have an object with infinite momentum because it would take an infinite amount of work in order to get it to infinite momentum. Since we don't have an infinite amount of energy to push on this particle with, then we cannot get its momentum to infinity. That means that if we were to graph time versus speed of some particle that I'm, say, applying constant force to, then we would find that it just approached the speed of light, but never got above it. This is why we call this the cosmic speed limit. Now, we're not going to go ahead and prove all of these things. I'm going to mostly just ask you to accept my word for it. But that means that this c, it is a speed limit, yes, for that particle that I was just describing that has some mass. That's true. But it turns out that c, the speed of light, it is a cosmic speed limit for anything any causal influence. In other words, information cannot travel faster than the speed of light. And nor can a spaceship or a rock or a bullet. None of those things can travel faster than the speed of light. But neither can any information, which is a sort of interesting thing. So this second bullet point here says, a causal influence can be any type of a particle, wave, or information that travels from A to B and allows A to be the cause of B. In other words, if I said, hi there, and you said, hello, then me saying hi and you saying hello back, those are two events which are causally related. I said hello, that caused you to say hello back, right? So those two events, right, are causally connected. And what this means is that there is no way for that information, like me saying hello, to travel to you any faster than the speed of light. It's pretty interesting. Now, this last bullet point is not something that we've gone into in this class, though we certainly could have. For two unrelated events, the relativity of simultaneity tells us that in one reference frame, A could happen before B, and in another reference frame, B could happen before A. I'm just going to tell you what I mean by that as opposed to going into an elaborate derivation. So here we have a situation. We've got star 1 and star 2. And let's say that both of these stars, they explode in a supernova. This observer right here, let's call him Observer A. Observer A is right in between these two stars at the exact midpoint. And he observes both of those explosions at the same time. The light from both supernova reach Observer A at the same time. Therefore, Observer A says, hey, both of those events happened at the same time. I know what's up. Star 1 and star 2 exploded at the exact same time. In other words, they were simultaneous. Now, it turns out, again, I'm not going to go through a huge derivation here. It turns out that Observer B here, which is moving very fast in this direction, will say, no, Observer A, you are incorrect. Star 2 exploded first. It's not just that he observes star 2 exploded first. I mean, literally, in his reference frame, star 2 exploded before star 1. Guess what? This guy, going that way, he disagrees with both of them. Observer C says, you're both wrong. Actually, star 1 exploded before star 2. And again, it's not just a perception, right? I'm not saying that, hey, the light from star 1 got to him before the light from star 2. No, it literally exploded before star 2, according to Observer C. So these events, star 1 explodes and star 2 explodes, there's no definite answer to which one happened first. They might have happened at the same time, or one of them might have happened before the other, depending on the observer. Now again, I'm not going to go into a whole lot of detail on that, or ask you any questions about it on the exam, but it is a true fact. This is only the case, though, if star 1 and star 2 are not, if those events are not causally related. What if instead I have, here's a satellite, looks like a TIE fighter. It's really a satellite. And there's satellite 1, and here is satellite 2. And satellite 1 explodes. And a little piece of shrapnel flies over here to satellite 2, causing it to explode. Okay, so now we got two events. Event 1, satellite 1 explodes. Event 2, satellite 2 explodes. These two events are causally related. Causally related. What that means is that to all observers, event 1 has to happen first, right? There's nobody that can think that event 2 happened first. No observer can observe event 2 happening first. Why? Because event 1 caused event 2. So we cannot destroy that causality. That makes absolutely no sense. For the previous example, those two events were not causally related, and so the order of those events will depend upon the observer. Now, what does this mean? If these two things are causally related, that means that this piece of shrapnel can never move faster than the speed of light. Okay, well, it doesn't even have to be a piece of shrapnel. What if This one exploded, and it had a self-destruct mechanism in it that sent out a signal, a radio signal, to this and caused it to explode. Well, guess what? That signal, that information, hey, I exploded, can never, ever, ever travel faster than the speed of light. It's pretty interesting. This actually puts a limit on the rigidity of objects. Right? If I take this object right here and I push on this side, guess what? This side moves. But how does this side know to move? I'm pushing way over here. Well, this side can only know that this side moved. There's a limit on how quickly that information can pass from this side of my hand, from this side of the object, to this side of the object. So if I go like this, you know what? Actually, this side and this side do not move at the exact same time. This side moves, and then the tiniest splittest of a second later, this side moves. Why? Because this side, the fastest the information can travel from here to here about the fact that we're moving is the speed of light, which puts a limit on how rigid this object can be. There must be a little bit of flexibility, because the fact is this side did not move at the exact same instant as this side. So again, this bold line here is the punchline. No causal events of any kind, a particle, wave, or other influence, can travel faster than the speed of light. And other influence could include information.